a lot of terms you need to understand in this chapter, and what we need to do is after understand the terms, then only we can solve the problems given. So every term here we will go through one by one. Okay, first one is, before we go to the semi-groups, you need to know first what is binary operation. Now I'm sure that before this in your secondary school, all the mathematics that you have learned before, you have done with the operation plus, minus, multiply, and also divide, right? So all these, when we do the operation, we must have two elements. For example, you must have 2 plus 3. So after that, you find the answer, right? And then you also must have 5 minus 2 to get the answer. So this one, we call it as a binary operation, where you have the operator in the middle, and you have the operands between the operator. So this is what you have learned before. But under this binary operation, what we have is, we also do with the operator and the two operands, but in this case, how do we want to determine that the binary operation is valid? So it will depend on what is the set is given to you. For example, if I say that now I give you a set of integer, and then the operator given is plus. So we want to determine, is the operator plus valid in the set of integer or not? So how to determine it is valid or not? What you need to do is, you just take any two integers, and then you use the operator plus, and you find the answer, see whether the answer is also from the set integer or not. Okay? So if I take any two integers now, I add up, do you think the answer will be integer also? Yes? Integer here means it can be positive and also negative, because I didn't give positive integer. If I write like this, means that it is positive only. So if I only put integer, then it will include negative. Okay? So do you think that any two integer after plus, you will get back integer or not? Yes, right? So if this happens, that means the plus here is a valid binary operation on the set integer. So how do we want to write? For example here, plus is a binary operation on integer. How do we want to prove that it is valid? So we cannot say, oh, 2 plus 3 equal to 5. 5 is integer, then valid. No, we cannot only use one example to show. We need to use any integer. So remember this? What is this? You have learned in your previous discrete maths, right? What does this symbol mean? What quantifier is this? Huh? All right. Okay. For all the A and B which belongs to integer, after I take the operator plus, it will belongs to integer also. So any two integers, after you add it up, the answer will belongs to integer. Then you can say that plus in the set of integer is a valid binary operation. Okay? So you can say that plus is a valid binary operation on the set integer. So remember, when you want to show that it is valid, you need to put any integer. Don't give a specific example. Okay? Now, if I ask you another operator, if I give you the integer positive with the operator minus. Do you think that this is a valid binary operation? Valid or not? Or the positive integer with minus operator. If I take any two positive integer and minus each other, do you think the answer will be from positive integer also? Not all. For example,
3 minus 4 will be end out in negative 1.
yes. So let A equal to 3, B equal to 4. So when we have A minus B, we will get 3 minus 4, which is equal to negative 1. So in this case, this is not belongs to integer positive. Whenever it is not valid, you can use a counter example to show it is not valid. But if it is valid, you cannot use an example to show it is valid. This concept you know, right? Correct? Because if you only show using the specific example that it is true, it doesn't mean that it will be true for all. So, if it is true for all, you need to use universal quantifier to represent any integer for A and B, and the answer also will belong to any integer. For this one, it is not valid because negative when you minus, it is possible for us to get a negative answer. So this is not belongs to integer positive anymore. Okay, so our conclusion is minus with the set of integer is not a valid binary operation. Okay, now you have the idea what is a binary operation here. Some more example. So we still have a few examples below. So when you say that the two integer add up just now like this, it is belongs to integer, right? The answer will belongs to integer. So we will say that the set of integer is clause under the operation plus. This is what we mean by the word clause. When you say that the set of integer is clause under the operation plus, meaning that whenever you take any two integers, the answer will be from the set of integer also. That is what we mean by the set of integer is clause under the operation plus. Okay? But if minus like this, integer positive, then you cannot say that the positive integer is clause under the operator minus. You cannot say that anymore. Okay? So if we look at the example 2, divide. Now we need to see the set given here is all the integers. Okay? If we take any two integer with the operator divide, do you think that the answer will come from integer also? No, right? Okay, so this is very clear. So we can just take any integer. A equal to 2, B equal to 5. So when we take the operator divide, we will have A divides B, which is 2 over 5. Then this one will not belong to integer. These two, the A and the B, you need to write like this, where each of them belongs to integer. Okay? Each of them is come from the set given here. But after we do the divide, then it becomes not integer anymore. So divide here is not a valid binary operation on integer. Okay, example 3. Union is a binary operation on a PS. What is PS again? Remember, you have a set S and you need to find the set of PS. What is PS? Who can remember? When do you study your discrete maths? Last semester, is it?
Last year.
Last year, which semester? First, second, third?
Second.
Third, third means still new, right? Now is your second year, first semester, right?
Second year, second.
Oh, your second semester. Okay. So, who still can remember this one? What is PS? Yeah, power set. Okay. What is the meaning of power set? If let's say I have a set S with 1 and 2, what is the power set? Means all the subset, right? So we will have empty set, set 1, set 2, and 1, 2. So this is the power set of 1 and 2. Now we want to determine, is this union a valid binary operation on power set or not? So meaning that if I take any two elements from this power set here and I do the union, do you think that I will get back the answer from the set S?
Yes.
Yes? Right? Okay, so empty set union with 1, you also get 1. Empty set union with 2, you get 2. And then empty set with 1, 2, you get 1, 2, and so on. So any of the element here union each other, you will also get it come from the set S. Right? So that's why union is a binary operation on the power set. Okay? So we can write for any A, B, this one is a set belongs to the power set. Then when you do the A union B, it will belong to the power set also. So not necessarily every time the operator, like this one, not necessarily every time it is not a valid binary operation. It will depend on the set given also. Like this one, when I say divides is not a binary operation on the integer, but if I change this one to the real numbers and not include the 0, then the divides will become a valid binary operation. Right? Because any number divide with any number except 0, it will be a real number also. Correct? So you need to see properly the set given with the operator. Okay, this one. Come to the conjunctive and disjunctive again. So here we have A belongs to 0 and 1. A has the elements of 0 and 1. And then the binary operation now is and O. So we try to combine this and see whether the n here is a valid binary operation or not. So 0 and 0 is 0, 1,
0,
1, 0,
0,
1, 1.
1,
Okay. 1, 0 or 0,
0,
1,
1,
1 or
1.
okay. So this is the N and O, the binary operator. And of course, we get the answer also belongs to the set A, right? So this is a valid binary operation on the set A. Now, in general form, when we want to write the binary operation, we will use the symbol of a star or asterisk in between the two numbers. So in this case, this asterisk actually is represent the operator. But in general form, we don't know what is the operator. We will just write it as the asterisk like this. Okay? So how do we want to say this? We can say this is a product of x and y. Or if they give you a and b, then you will say this is the product of x, a and b. So the operator, it will be given, the question will give you whether it is plus, minus, union, and, or, intersection, and so on. So whatever operator given, it will be replaced by this asterisk here. Okay? So the asterisk is just a general form. Now, after you know what is a binary operation, the next one is we go to the associative again. Remember what is associative law? If let's say I have plus, is this associative or not? Plus. Associative means we need to have 3 elements, A, B, C, and then we will do A, B first, then plus C, and then find the answer of B plus C, whether these two answers are the same or not. Will these two answers be the same? If I do the A plus B first, and this one is I do the B plus C first, finally answer same or not? Same, right? So in this case, we will say that the plus here, the operator plus is associative. Okay? So whenever you say that it is associative, the answer you find from here must be the same, no matter you do which part first. Okay? So for the binary operation also the same. If they give you like this, the asterisk means that this one will represent the binary operation. If it is associative, means that these two will be the same answer. Okay? So we can give the bracket here. If it is the same, either you put a bracket or not, it doesn't matter already. Because which part you do, the answer also will be the same. So the example here, you can put the plus. X plus y plus z is equal to x plus y plus z. What other? Do you have any other operator that it is associative? Beside plus? Minus associative or not? A minus B minus C, is it the same with A minus B minus C? Same or not?
Yeah.
No, not same.
Example?
Double negative equal to equal.
the answer at the left?
-4.
Left side. 1 minus 2 is? -1 minus 3?
-4.
This one?
The inheritance is 2.
2. Agree? Okay. So, these two are not the same, right? That means minus is not associative. Okay? And is n associative? These two same or not? So this one, when you do either 1 and 0 first or 0 and 1 first, then you will get the same answer also. So for n, it is also associative. Same also for OR, and then multiply. So all these are the example of associative. Okay? So now remember, if you want to show that something is associative, you need to prove like this. Using the general form and represent your x, y, z by the set given. If the set given to you is an integer, then you need to say for all the x, y, z belongs to integer, this x plus y plus z is equal to this. Okay? That is how we show that it is associative. So meaning that to show associative, we must have 3 elements. Remember, associative, you must have 3 elements. Now, come to the commutative. Commutative is xy equal to yx, which means it is only involve 2 elements. A plus b is equal to b plus a. Right? A multiply b is the same with b multiply a. This is commutative. What else? Any other elements? A and B equal to B and A.
A or B
A
equal to
or
B
B.
or A.
Yes, equal to B or A. Any more? Have others like A union B equal to B union A intersect B equal to B intersect A. So all these are the commutative operators. So now you already know what is a valid binary operation, what is associative, what is commutative, right? Come to the term in this chapter here, which is semigroup. Now, what is the meaning of a semigroup? If let's say you have a set given, and with the valid binary operation, the operation is associative, then we will say that the operator with the set given is a semigroup. Okay? So you need to combine all the conditions that you have learned just now to say that it is a semigroup. It is a valid binary operation with the associative property. So the binary operation must be associative, then only you can say that the set given is a semigroup. So this is the general form of the binary operator, this asterisk here. In order to show that it is associative, so we write it like this. And the elements of x, y, and z must be belongs to the set given. In this case, set S. Okay, we give a general variable for the set here, which is the set S. So again, if it is associative, as I said just now, you put the bracket or not, it will not affect your answer. Because any parts you do first, both side answer will be the same. So we look at the example 7. The set given now is a positive integer and the operator given is plus. So we want to determine now, is this set positive integer with plus can be a semigroup or not? So before you can say that it is a semigroup or not, what do you need to determine? What do you need to determine in order to say that it is a semigroup? The condition I said just now is the operator must be associative, right? So you must determine the plus here, is it associative or not? Now we already know that plus is associative, so how do we want to show it? So we need to show that for all the A, B, C, which belongs to integer positive, A plus B plus C will be equal to A plus B plus C. This is to show that this plus is associative, and to show that the set given is a semigroup. Okay, so we can make a conclusion saying that the set of integer positive with the operator plus is a semigroup. Okay, so this is the method. How do we want to show that it is a semigroup? Now, another example is L is a lattice. Now, if the set L given now is a lattice, we need to show that the operation OR is associative. Then only we can say that this set is a semigroup. Anyone know what is lattice? Now, lattice means you have learned the partial order set before, right? Hash diagram. Remember? Okay. So for the hash diagram, let's say I have this one. Let's say I have this diagram. When I put the element A, B, C, D, I find the two elements here. I try to find whether they have a greatest lower bound and least upper bound or not. So if any two elements here, we can find their least upper bound and also their greatest lower bound, that means this is a lattice. So another way to say is a lattice is a set where you can find any two elements with a greatest lower bound and least upper bound. So, if let's say I take A and C, if I take A and C, what is the greatest lower bound? Greatest lower bound for A and C? A. Greatest lower bound for A and B? A. For B and C? Greatest lower bound for B and C? A. Greatest lower bound for B and D? B. C and D? C. So that means any two elements also you can find the greatest lower bound, right? Now you find the least upper bound. A and C, least upper bound? C. A and B? B. B and C? Least upper bound. B and C? Huh? B or D? Donkey or boy? Donkey, right? Least upper bound for B and C is D. Least upper bound for B and D? D. C and D? D. So, any two elements here, we can find their least upper bound also, right? So that means this is a lattice. Okay? Then what happens if we have this diagram like this? A, B, C, D. What is the greatest lower bound of C and D? Greatest lower bound of C and D? A, B, C, D. Which one? C. Correct? Greatest lower bound is C. What is the greatest lower bound of A and C? Huh? A and C. Greatest lower bound. Or you find the lower bound first. What is the lower bound of A and C? You forgot everything already, ah? Huh? Yes, ah? Means forgot. Then you return to who? Did I teach you before? Then you return to me already. Then I teach you back again now. So the greatest lower bound of A and C should be C, right? Because the lower bound of A and C will be C and A lah. Right? So out of the A and C, the greatest is C. So that's why the greatest lower bound of A and C is C. Remember, we say that the point must be less than or equal to, right? So the C now is less than or equal to C itself. So that's why when you find the lower bound, you need to include the C also. And out of A and C, the greatest is C. So same also for the B and C, the greatest lower bound will be C. Right? Okay. Now, what happens if I take the A and B? What is the greatest lower bound? A and B. What is the lower bound of A and B? Don't have or don't know? Don't have lower bound, isn't it? So, since the A and B here, no lower bound, meaning that they don't have any greatest lower bound also. So, if they don't have greatest lower bound, means that this is a lattice or not? No. Okay? So, this is the example that it is not a lattice because we don't have a greatest lower bound for A and B. And this is a lattice because we can find all the two elements can have their greatest lower bound and the least upper bound. So this is lattice, huh? Okay. Now, under the lattice here, we can use the operator OR, and we need to determine whether this is a semigroup or not. So, to determine a semigroup, we already know that OR is associative. Then, you can say that the set L, which is the lattice, with the operator OR, is a semigroup. So now you know what is the example of semigroup already, right? You have the lattice here with OR, you have the set of positive integer here with plus. This is the example of a semigroup. Okay? As long as you are able to determine that the operator with the set given is associative. Now, another example, if let's say you have a set A, the A here is a set of symbols inside. A string represent the string form from the set A. For example, if let's say my set A, I have A and B, and then I want to form a string from this A. So, what are the strings that we can have? First one, let's say I have alpha. We have the string of AA. Beta, I have the string of AB. Gamma, I have the string of BB. So now I have 3 here. And I want to determine is this associative or not. Do you think the joining of the string is associative? Let's say I want to join alpha and beta and gamma together. I do these two first. Is it the same with alpha, with beta and gamma first? Answer same or not? We try to solve using the one I give here. How is your answer?
Same.
Same, right? Okay. So that means the joining of the string is associative also. So when we want to show that this is associative, you can just say for this one is a string form from the A string. Because the A string is a string that we get from the set A. So we will just say for all the alpha, beta, and gamma, which belongs to the A string. The alpha join with beta, and then join with gamma will be the same with So we can conclude that the set A as string. The set A as string, which is a string with the operator of joining of the string, is a semigroup. Now, when we find this semigroup, there is a specific name for this joining of the string. We will call this as a free semigroup. So we call this free semigroup. Generated by A. From the set A, we get all the string. The A as string is a set represent the string, and we take any three strings. If you do it using the joining of the string, then it will be associative. So this is a semigroup also. Okay? When we say the joining of the two strings, we will use this symbol, this and symbol, to join the two strings. And the word that we use for the joining of the string is a concatenation. When we say concatenation, you need to know it is the joining of the two strings. Okay? This one is the word. So it is still the same concept like the semigroup. The only thing we have is we will have a specific name for the joining of the string. We can call this as a free semigroup. Okay? Only the name a little bit different. So we have done with the example for semigroup. Any question for this? All of you, this one, all of you get the answer understand, right? Both sides. Nobody get different, So you just join these two together first, AA, AB, then join with BB, so final answer will be AA, AB, BB. This one you join the AB, BB first, then join with AA, so the final answer also AA, AB, BB. So they will be the same. Okay? Now you can take